started. Welcome. My name is Damon Mullis. I'm the Executive Director and Riverkeeper here at Ogeechee Riverkeeper. We're a 501c3 nonprofit, and our mission is to protect, preserve, and improve the water quality of the Ogeechee Basin. That includes the Canoochee and Ogeechee rivers, all the coastal rivers in our basin, all the tributaries that feed all those rivers, and also the groundwater that sits under our basin, which leads us to why we're here tonight. If you're attending, you're probably well aware that due to the Savannah Port expansion and the development of the Bryan County Hyundai facility, our region is experiencing unprecedented industrial development and population growth. This will dramatically increase the demands on our water resources. The Floridan aquifer historically has been the major source of water for our region, but due to overuse along the coast, the state has restricted the amount of water that can be withdrawn for the aquifer in certain areas. Recently, proposals to drill additional Floridan aquifer wells just outside of that restriction zone to service interests within the restrictive zone have been proposed. These include 4 groundwater wells in Bullitt County to supply water for the new Hyundai facility, a new drinking well in Long County to serve the city of Hinesville, and we've heard that industry in Liberty County will be proposing a new well in McIntosh County to supply their growing needs. These proposals and the practice of drilling outside of these restrictive zones has increased concerns that we're not using the Floridan aquifer sustainably, and people are concerned about the possible negative consequences of that. So we've asked Dr. James Reichard to attend this evening and explain what and how the Floridan aquifer works, and then answer questions that the public may have about these proposals and what impact they may have on the sustainability of the aquifer. So Dr. Reichard has a BS and MS from the University of Toledo and a Ph.D. from Purdue in geology. His early research involved modeling the effects of pore pressure changes on groundwater, flow systems, and on developing computing applications for aquifer tests. Since coming to Georgia Southern, his attention has shifted towards applied hydraulic research on the Georgia coastal plain. His current research involves identifying permeable pathways within the coastal plain that allow groundwater to flow vertically between aquifer systems. If you have any questions for Dr. Reichard, you can put them in the Q&A. There should be a button down on the bottom of your screen. And Dr. Reichard is going to do a short presentation for us, and then we'll open up to questions, and we'll go until we run out of questions or we hit 8:30. So Dr. Reichard, thank you for joining us and supplying us with your academic and scientific expertise on the issue. And I'll turn it over to you for a short presentation.
Okay, thanks, Damon. Thanks for the nice introduction, and it was a good overview of the situation that we face in the coast. You explained it very well, the demands on our water resources. I will, before I start, I would like to mention that in addition to my role as being on the faculty at Georgia Southern, I was also one of the founding board members of the Ogeechee Riverkeeper, which was the Canoochee Riverkeeper back in the early 2000s. And I'm currently on the board of the Center for Sustainable Coast with David Kyler as executive director. Tonight, I'm going to give you a brief overview of the science we call hydrogeology, which is the study of the movement of water through the subsurface. Then once we have a little basic understanding of that, we'll be able to talk more about the upper Floridan aquifer system. That's our main water supply in coastal Georgia. Then we'll look at some of the potential impacts of proposed wells in Bullitt County. This presentation should run about 15-20 minutes, so we'll leave plenty of time for your questions. So we'll start off with asking the question, what's an aquifer? Let me tell you what an aquifer is not. It's not a large underground pool or cavern that you can go scuba diving in. Okay? Those type of aquifers do exist, but they're the exception rather than rule. This is an aquifer. It's a highly porous and permeable rock that water can move through and from pore to pore. So there are aquifers that you go swimming in, but for the most part, they're granular materials like this. So we can define an aquifer as a layer of rock or sediment that has internal pore or void space that allows water to move from one pore space to another. So we say it's capable of transmitting water. The best aquifers are those that are made of granular material, like grains of sand or grains of coral or limestone. Okay? They hold lots of water. There are systems that are where the water moves through fractures, like in fractured granite that's common in North Georgia. The problem with these types of aquifers, they just don't hold much water. Then there are cavernous limestones that do form, but these two here are more the exception rather than the rule. Again, the most common form are granular materials because water moves very easily and there's a lot of it. In contrast, clay-rich materials, they hold a lot of water, but water just can't move through this material because the tiny clay particles hold onto the water molecules so tightly. So it's what we refer to as being impermeable. That leads us to the two hydraulic properties we talk about: porosity, how much water an aquifer can hold, and its conductivity or permeability, how easy water moves between those pore spaces. To help you relate to this, I put up the porosity and conductivity values of some materials we're all familiar with: gravel, sand, and clay. We see that clay holds about twice as much water as sand and gravel. But what's really important for an aquifer is to get the water to move through it. So that we look at the conductivity. You don't need to know what these units mean, but if we look at the difference between these units here, that's 3 orders of magnitude, which means water moves through gravel 1,000 times faster than it does through sand. There's 6 orders of magnitude difference between sand and clay, which means water moves 1,000,000 times faster through sand than it does clay. So we call an aquifer something that's highly permeable or conductive, things like layers of gravel, sand, limestone, or fractured rock. We call things that don't allow water to move through them very easily aquithards, okay? Things like layers of clay, shale, muddy limestones, and unfractured rock. I've used this illustration so we can talk about the 2 types of aquifer systems. In this diagram, we have 3 aquifers, 1 at the top and 2 at the bottom. The one at the surface we refer to as being an unconfined aquifer because it's open to the Earth's atmosphere. When you drill down into an unconfined aquifer, eventually reach the point where all the sediment is saturated. We call that top of the saturation zone, the water table. In contrast, these other 2 aquifers we refer to as being confined because they're sealed or sandwiched between layers of aquitard, these low permeability clays. Because these are sealed off from the atmosphere, that means you can pressurize these aquifers, much like the tires in your car. We can pressurize those with water. So when you drill down into a confined aquifer and you breach through the confining layer, aquitard, this water under pressure is going to rise up into the well bore until it's equal to pressure in aquifer. We refer to this level of pressure as the potentiometric surface. It measures the amount of pressure. And we refer to wells that are in confined aquifer as being artesian. If your artesian well happens to the top of it lie below this pressure surface, you get what we call a free-flowing artesian well. This illustration shows a pressure surface above landscape for this confined aquifer. Right? So anywhere you drilled here, you would have a free-flowing artesian well. One of the things I want to point out here is that these systems, these big regional systems, are quite vast. And one well here is like a tiny pinprick in this big aquifer. So it bleeds off a very small amount of pressure. However, you start putting in large numbers of irrigation wells or large industrial wells, you can bleed off a substantial amount of pressure from the aquifer, and the surface can begin to lower. Here is a photo of a flowing artesian well where the pressure surface is above landscape. On the right is a highly pressurized well that was drilled into the High Plains Aquifer in the Great Plains in South Dakota. Here, the pressure surface, when this picture was taken in the early 1900s, pressure surface was 90 feet above landscape. Since this photo was taken, over 170,000 irrigation wells have been installed throughout the Great Plains, and the pressure has been declining ever since. And in some places, it's below land surface now, and it's as much as 120 feet and still dropping in some areas. So this idea of depressurizing these systems is just like getting a lot of leaks in your tires. Let's quickly talk about the direction that groundwater flows. It simply flows from areas of higher elevation to lower elevation. So if you have a water table and it's sloping, we know it's going to flow from left to right because that's the direction of the slope. Because the height of the water here is directly related to its water pressure, we can also think of this as flowing from high pressure to low pressure. Wherever there's high water levels, there's high pressure. So water is going to flow from high pressure to low pressure. We use this same principle to discuss how water moves between aquifers. Okay, we call this flow across an aquitard as leakage. So in this example, we see here's the pressure surface of the confined system, and here's the water table. Because the water table is higher, it has higher pressure, and that forces water to leak downwards across the aquitard. If we have a highly pressurized confined system where it's above the water table, that means water that's higher pressure down here is going to leak upwards. We call this upwards leakage. Here's a illustration I use for my class and for my book that shows that groundwater moves in complicated paths. It moves both horizontally and laterally and vertically. In this case, everything's flowing to the right in the aquifers, but in some areas we have leakage downwards into the confined aquifer. In some places we have leakage upwards to the surface environment. Now, let's talk real quick about how fast groundwater moves. For this, we use what we call Darcy's law, which simply states that the velocity of water is directly related to how permeable or conductive the aquifer material, how steep the slope is of the water table, and it's inversely related to porosity. If we plug in values of conductivity and porosity that I showed earlier and use an average slope, we see that water moves through a typical sand aquifer at about 1 foot per day. Now, this may seem slow to you and me, but in terms of a groundwater system, this is moving quite fast. And so to travel the distance to 50 miles from Statesboro to Savannah, an aquifer at this speed would take 725 years. Okay. Keep in mind, that's fast for an aquifer. If we plug in values for clay that I showed earlier with the same slope, we see that water moves exceedingly slow through clay, okay? Very slow. And for all practical purposes, it would never make it to Savannah. Okay, it's 290 million year travel time. So clay does not transmit water very well. I put this illustration here because we're going to talk about wells. This is a typical domestic water well where the pumped water is forced into a pressure tank at the surface. That's how you get pressure to go into your house. So when a driller drills a well, they use a drill bit or an auger, and they bore down to the desired depth. Then they drop either a steel or PVC casing down the hole to keep it from collapsing. At the bottom of the pipe, there's a screened interval that lets the water in. Then they pack sand around the screen. They use a clay seal, and then for the rest of it, they put concrete all the way to the surface. All this is designed to keep contaminants from the surface from running down your borehole. And then at the final step, they drop a submersible pump, an electric line, and a pipe up to the top. So that's your typical water well. When you turn on a submersible pump, it draws water in through the screen from all directions, creating a radial decline in water pressure within the aquifer. We refer to this radial decline as a cone of depression. It takes the shape of an inverted cone. Okay? Clearly, the more you pump, bigger the cone. Okay? And also, the deeper and wider the cone gets, the more you pump. Also, where two cones overlap, the drawdown is cumulative. I should mention that the more conductive the aquifer material, if you get something really conductive, the cones are less deep, they're shallower. I put this illustration here to point out that we can get cones of depressions both in the water table and the potentiometric surface that may lie over the landscape. Okay. This is an imaginary surface, but it still has a pressure decline that takes the shape of an inverted cone. I also will point out when you pump a confined well, because the overlying aquitard, any contaminants at the surface, it's protected from by this clay aquitard. All right, now that you know a little bit about the science of hydrogeology, we can talk about the upper Floridan aquifer system here in coastal Georgia. South Georgia is part of this large sedimentary sequence we refer to as Atlantic coastal plain. Within the coastal plain, there are many aquifers, but the most important one and the most prolific is the Floridan aquifer system. It's a series of highly conductive limestone layers that come to the surface near the fall line, where water enters the system, and it leaks downwards. And then once it's in the system, it flows laterally underneath the coastal plain. And then it gets to the coast. The pressure forces it to leak upwards and eventually discharges in the marine environment. That sample that I showed earlier, This is the actual sample of what the Floridan aquifer. We collected this in places where the rocks come to the surface, and you can see it's highly permeable, and it's got a lot of porosity. This rock is about 40 million years old, and it's full of marine fossils. This is a U.S. Geological Survey cross-section through the coastal plain, showing the three main permeable zones of the Floridan. The Floridan is not a single layer, but it consists of three main permeable zones. The lowest and the most saline is the Fernandina. Then we get a little bit fresher, it's lower Floridan. And the thickest and most fresh is the upper Floridan. This is what serves all of coastal Georgia, like the Floridan aquifer. Above its upper confining unit, we collectively refer to these sandy layers up here as the superficial or unconfined. Before we began major pumping withdrawals, the pressure in the Floridan was above landscape, so we had free-flowing artesian conditions on barrier islands and up and down the coast. This is a USGS contour map showing the configuration of the pressure surface in 1880 before we began major pumping withdrawals. Right? Blue areas where we would have free-flowing artesian conditions. So anywhere you dropped a well into the Floridan in this blue area, you'd have free-flowing well in 1880. And if you're a water molecule in 1880, you would have flowed underneath Bullock County, and you would end up discharging out into the marine environment north of Hilton Head Island in Port Royal Sound. This is a USGS map from 1986 showing the development of this very large cone of depression centered about Savannah because of the municipal industrial withdrawals. Water that used to leak upwards and along the coast has been reversed. It now flows downwards. And so look at the amount of blue area that has been shut off. So we've lost a lot of artesian pressure. We've depressurized the aquifer. Now, if you're flowing underneath Bullock County, you're going to get swept up in the cone of depression in Savannah. Because of this loss of artesian pressure, we've had modern seawater enter into the aquifer at Hilton Head Island. We call this lateral saltwater intrusion. Here's Hilton Head. This is a cross section parallel to the coast. So we have Savannah down here, Hilton Head, and Port Royal Sound. What happened was the aquitard here was breached by rivers during the last ice age. So it was cut away. So the aquitard is missing at Port Royal Sound. So when the aquifer was fully pressurized, this was like a major leak in your tires that was just blowing fresh water out into the marine environment. This was a major discharge point. And there were large freshwater springs coming off the seafloor. Spanish ship captains wrote in their logs that they would resupply their ships with fresh water while anchored in Port Royal Sound. Sounds crazy. This is a photo from National Geographic showing a large freshwater boiler spring coming off the limestone bedrock in the Yucatan Peninsula in Mexico. This is what our springs probably looked like in Port Royal Sound before we depressurized it. The photographer here used a lamp to backlight the spring so you could see it. So these were prolific discharges of freshwater in the marine environment. We look at the same cross section today. Well, now we've depressurized the system. We have this huge cone of depression in Savannah. What used to be a discharge point for water is now an entry point for seawater. And this is why the wells in Hilton Head have been salting up. They've lost most of their Floridan production wells because the saltwater is moving laterally. Okay, in addition to the lateral saltwater intrusion at Hilton Head, we had vertical saltwater intrusion occurring at the smaller drawdown cone in Brunswick. This is a map showing the Brunswick Peninsula two major pumping wells. One is related to municipal supply and the other is a paper company. And the colors represent the chloride concentration in the upper Floridan or salt content. This is a saltwater intrusion. Based on the shape or geometry of these plumes in the pumping centers, the U.S. Geological Survey concluded that there's some type of vertical conduit, like a fault, that's allowing, at these two places, it's allowing saltwater to move up from depth and into the pumping horizon. To give you a better idea what this looks like, here's Brunswick, here's that conduit. We're looking parallel to the coast from St. Mary's through Savannah to Hilton Head. And this rock unit here is all the limestone of the Floridan aquifer. Based on geochemical and isotopic data, the USGS determined that the saltwater is coming from the Fernandina permeable zone. This is a distance of over 2,000 feet. So this is a major conduit that the only reason we know it's there is because we just happened to place some industrial and municipal pumping directly over that. Yeah. So that is what's happened. We call it upconing. All right, with that, let me quickly mention some of the work my colleagues and I have been doing on St. Catherine's Island for the past 12 years. Like all barrier islands, St. Catherine's is a large unconfined aquifer that sits on top of the confined Floridan aquifer. Before we began depressurizing the aquifer, we had leakage upwards, so we had all kinds of artesian springs along the coast and on the barrier islands. Today, we depressurize the aquifer, water no longer comes up, it leaks downwards. This is just a LiDAR map showing the wells we have on St. Catherine's. We've been monitoring 4 upper Floridan wells that the island uses for water supply, and we installed a series of shallow wells in this unconfined aquifer. Then for reference, this is another version of the drawdown map or cone of depression map that USGS has created. In this one, I drew groundwater flow lines showing the path that water takes. And red indicates those pathways that have the potential to bring saltwater, modern seawater into the system. Okay, there's the one we know is already happening. All right. My colleague, Kelly Vance, started doing the work in the early 2000s, running ground penetrating radar surveys over St. Catherine's extensive dirt road network. One of the things that he found quite often were these sag features in the shallow subsurface sediments, about 15 to 20 feet deep. The way we account for these sag structures that we see is we believe that what's happened over time, groundwater used to flow upwards along fractures and faults. Over time, it would dissolve out caverns in the limestone of the Floridan aquifer. Over time, some of these would get large enough to collapse and create these sag structures. These sag structures are important because they were vertical conduits, similar like the breach I showed at Hilton Head, that allowed fresh water from the Floridan to gush up and form springs on our barrier islands. Okay. Now that we've depressurized the aquifer, the flow is no longer up, it's downward. So these conduits can allow water from the surface environment to go down into the Floridan. Okay, now let's talk about what you're here for, the potential impacts of those proposed wells in Bullock County. For this, I thought it'd be useful to show you the completion diagram, a sketch of what one of Georgia Southern's upper Floridan wells. Okay. We have, I think, at least 2, maybe 3 wells that we use on the campus for water supply. In the city of Statesboro has similar wells. So almost all wells in the area of city of Statesboro, the proposed wells down in Southeast Bullock, all pretty much have the same geology and construction. So this well here in Georgia Southern is 600 feet deep. Okay. So they reached the top of the aquifer at 400 feet, and they went down another 200 feet to the bottom of it. So the aquifer here is 200 feet thick. Above that are 300 feet of clay-rich sediments that act as an aquitard or confining layer. Because this well is pressurized, the system is pressurized, water rose up the casing, and its static water level is 125 feet below land surface. So that means there's 275 feet of water above the top of the aquifer. That's how much pressure is in the system. During their initial pumping test, they pumped the aquifer, this well, at 0.9 million gallons per day, or 900,000 gallons per day. And they reached the static drawdown, created a cone of depression, and it dropped 55 feet from its static level. I don't know how far out it went, okay? For comparison, 2 of the proposed wells for the Hyundai project are rated or capacity of 3.1 million gallons per day, or roughly 1.5 million per day. So that's about 1.5 times this single well at Georgia Southern. So their wells are fairly comparable, okay? About 1 million gallons a day, 1.5 million. Right. So what are some of the potential impacts? Well, number one, around the proposed wells in Southeast Bullock, there will be a drawdown cone. There'll be radial decline in water. And some owners, well owners that have existing submersible pumps in their Floridan wells, they may need to lower their submersible pumps to reach new water level. I'll just say that when you have a well like this, you don't put the pump all the way down here, because then you have to pay the electricity, and it takes a lot of effort and energy to lift that water to the surface. So typically what a driller will do was put the submersible pump a safe distance down, but not all the way down, because it saves a lot of electricity. So if you happen to be close to one of these the proposed wells, you may have to lower your submersible pump, okay, to reach that. So that involves some cost. That is a very likely possibility for people who are in close proximity to one of the proposed wells. One thing I can say that's not going to happen is the Floridan aquifer is not going to dry up by any of these wells. They're large capacity, but they're not, super giants or anything like that. Remember, we still have, even if we draw down 75 feet, there's still 225 feet of water above the top of the aquifer. So the aquifer is going to remain fully saturated, okay? But it will become depressurized. That does present some other problems, but the aquifer is not going to dry up. Another thing to keep in mind, the well owners will not have to deepen their wells. If you have a Floridan well, that means that your well goes down into the limestone. And where the submersible pump is placed is another issue. So the wells don't have to be deepened. We'll just simply have to lower, I'd say simply, it'd be costly still to have, somebody has to pay for this. You have to lower your pump, but the well itself does not have to be deepened. Another thing that people have mentioned, that they think that surface streams and ponds will dry up. That is very unlikely to occur because we have 300 and some feet of very low permeability clay-rich materials overlying that. So there's very little hydraulic connection between what goes on down here and at the surface. They're two separate systems, and there's a lot of insulation between them. But another thing that I've heard mentioned many times is that saltwater intrusions are going to occur in our wells. I can say unequivocally that saltwater from the ocean is not going to make its way to Statesboro and Bullock County. Okay, to do that, it would have to flow uphill or up the hydraulic gradient, which is physically impossible. Water flows from high pressure to low. Okay. What can happen, and one of my concerns that I voiced to EPD and then on Facebook to some of the groups that you may have read, is that we could get vertical saltwater intrusions similar to what's happened at Brunswick. If any of the proposed wells happen to be lying near one of these hidden vertical conduits, okay? So generally water doesn't move vertically unless it has some pathway. So that's the idea here. So we could get some vertical saltwater intrusion if there's a hidden pathway near one of these. And we don't know in advance whether that, no other advanced ones was there. So again, going back to our experience with St. Catharines, what does this look like? Well, these sag structures are related to subsurface collapse. And what we call these things are normally a sinkhole. It's a sinkhole. Sinkhole can create a vertical conduit. To give you an idea what some of these look like, this is one that we investigated in 2019 that started to open up near Register. You can see these circular scarps. So this is the beginning of a sinkhole. I've been told that since this picture was taken, some of the outbuildings here have actually fallen in. This is greatly enlarged. I plan to get out there and take another picture. Here's one near Middle Ground that we investigated in 2010. This was a complete collapse. It happened almost overnight. Remember, depth of the limestone is 400 feet. So a large cavern in the upper Floridan collapsed, and then it propagated all the way to the surface. So what you're seeing here is a vertical conduit down to the Floridan aquifer. So this is a way in which the water can communicate very easily from the surface down to the upper Floridan. Okay. Now this may look large. Oh, I want to say, this is with the concern that one of these features would lie hidden close to one of the proposed wells. Now, for another perspective, this is that same sinkhole from the air. Now it looks smaller. If we go to landscape scale, there it is. Here's the Ogeechee River. Okay. So these things are very small features, okay, but they're important. They're avenues for water to move vertically through these systems, and they can cause saltwater contamination. Now, I've only found 2 of these in Bullock County, but I guarantee you there's a lot more of them that we don't know about. Okay, they're just a common feature. Now, the chance that one of these wells would be right next door to one of these conduits is not high, but it's something that we need to take into consideration. EPD is already, looks like they're going to take some of the recommendations and monitor these wells. Finally, we'll get to this last slide here. Some of you heard about the EPD's water management plan for managing the saltwater intrusion in the different zones, the red zone, yellow zone, and we're in the green zone. In the red zone, they have a moratorium on any further water withdrawals from the Floridan aquifer because it directly will impact the pressure decline in the center of the Kona Depression and accelerate the saltwater from Hilton Head moving in. Yellow, they will allow some additional pumpage, but it's limited. That's because they're a little bit further away, and it's further away from the source area. The rest of this we refer to as a green zone because what happens out here has less bearing on the saltwater intrusion. We're on the opposite side of the Kona Depression. So, and I've heard people say this boundary is very arbitrary. It has nothing to do with the aquifer. There's no hydrologic barrier here. So why do we have this boundary? I don't know the details what went on this decision, but I can pretty much guess it's because it's easier to manage the water resources by county than it is some arbitrary line that goes through. Okay, because it's easier for them to manage. Okay. And with that, that's all I have for you. I wanted to leave the rest for questions. And Damon, I'll send it back to you.
Well, thank you, Jim. That's very, very informative. I learned a bit myself, and I thought I knew a lot about this. We do have some questions already, and I have some of my own, or some that other people have submitted ahead of time. So as a reminder to anybody that joined late, if you have a question, there's a Q&A icon down at your bottom. Just put your question there, and we will kind of go back and forth between questions I have and the questions that participants have, and we'll go until we run out of questions or we hit 8:30. So I want to start with one that I had personally, and it kind of goes back to a little bit about what you talked about with the potential of saltwater intrusion. You mentioned that you know, the Bullitt County and these wells are drilling for the Hyundai site are really far away from the coast, so potential of saltwater intrusion from the coast or the ocean is virtually impossible. But you mentioned there was this potential for saltwater intrusion vertically, and I think that can you talk a little bit about where that comes from? And I think that comes from other aquifers that are below the Floridan. So I'd like to hear a little bit more about that, one, and then two, so why, if we have all these other aquifers, why do we pretty much just utilize the Floridan and don't try to use these deeper aquifers that may not have the same pressure and demand on them? So
okay, let me go back to share my screen real quick.
Sure.
I won't go pull up all the detailed slides, but I can point to this if you guys folks can see this well enough. I'll go to this. Hang on a minute. Okay. As I mentioned, as you go down deeper into the surface, the water gets more saline. And so the reason we use the Floridan is twofold. It's closer to the surface, so it takes less electricity to pump it out. And remember, electricity has, just like you carrying rocks or something up a set of stairs, it takes effort to carry this up. So the closer you are to the surface, the less energy. So one of the reasons is it's lower cost. And the other is that the water's fresher. It's much higher quality. So as you go deeper, the lower Floridan is a little bit more saline, but it's still drinkable. You get down here, the water is undrinkable and it's very salty. Okay. And the source of that saltwater intrusion is shown here. It's coming from some of these deeper aquifers. So the concern that I'd raised was if you have a pumping well close to one of these conduits, you can draw some of this more saline aquifer water up. Okay? Oh. And it's also possible to draw water from the surface down as well, because that sinkhole goes all the way to the surface. So if you have something undesirable up at the top, you could bring undesirable water into your aquifer. Yeah. I will mention this too, because people, Damon, you even asked me this the other day. Why don't they just use water from the river? One of the reasons the paper companies like to use Floridan aquifer water, because it's the same consistency, same quality day in, day out. The quality in a river it changes daily with the amount of discharge and sediment, and it's got all kinds of things in it. So from a quality point of view, it's very consistent and it's much cheaper. So as much as we want them to use surface water, it's an economic choice. Economics plays a big deal in that.
Yeah, I'll follow the money, right? As they always say. All right, so let's go to some of the participants' questions. This one ventures a little bit on policy, which I know you're not here to talk about, but I'll go ahead and ask it, and maybe I'll answer it. Do farmers have an absolute right to the Floridan aquifer, and how would this impact industrial development? I would say, yeah, I'm not sure I can quite answer that, but I do know the state, particularly in the west part of the state, with the Florida, Georgia, Alabama water wars is really kind of limited and had some restrictions on how much agricultural withdrawals were permitted. I think just recently, this week, there's some movement on relaxing that. So I don't think they have an absolute right. I think the state does have some regulatory authority there. And, you know, any impact to the aquifer, whether it's industrial, agricultural, or municipal, has some, you know, impact to development. Anything you want to add there, Jim? I know you're not here to talk about policy.
No, and I'm not an expert in water law. I think people are thinking about the mineral rights and water rights. What's on your property is yours. But in this case, it's a shared resource. It's a shared public resource, and the state is, I think, views that their responsibility to safeguard this public water resource, because obviously what's flowing under your property today is flowing to somebody else's property tomorrow. And so it's a shared resource, and that's that I think is where they get their authority to manage the water supply.
All right. This is a little more scientific. How much of the coastal plain is aquifer recharge area? And this kind of goes back to, I'll elaborate a little bit on this because I have a similar question, relatable question, is ultimately all of these aquifers are recharged by rainwater, right?
Correct.
And so talk a little bit about the recharge areas, how those work. And then personally, I just had a question, you know, how has the Floridan aquifer remained so pristine and clean? Because I know the state and a lot of organizations like us, you know, spend a lot of time and energy trying to protect the recharge zones that we're aware of. I assume they're recharge zones we're not aware of. But even atmospheric deposition of mercury and PFAS and all these other things that, you know, are essentially in the rainwater. How has the Florida aquifer stayed so pure and clean with all these threats and that sort of stuff?
Yeah, that's a good question. Let me go down to this view here. So most of the water enters the system along the fall line. This is where these units come to the surface. So the Floridan aquifer is 400 feet below land here. And as you get closer to the fall line, eventually comes to the surface. And that's where most of the water enters the system. Just will say before I leave this slide, so water that we're drawing from Statesboro, the travel time for it to get here is about 1,500 years. So the water that we're drinking today that I pull out of the tap last saw the light of day about 1,500 years ago when it entered through the fall line. It's one of the reasons our water quality is so high. There was no, you know, humans influence in that water. So it's been, and plus it goes through the grains pore space of the aquifer. So we got about 1,500 foot travel time. Now let me answer this question a little better by going back to this. This is very similar to our system here. So we have the Floridan aquifer. It comes to the surface near the fall line. So most of the recharge, the recharge area for the Floridan is mostly along the fall line where these units come to the surface. In fact, that's where we collected the sample that I showed you, where it comes to the surface. Okay. But it does, USGS has done modeling studies where they know that not all the water is coming through here. There is leakage downwards through these confining layers as you get, and it goes upwards. So a certain component of it, I don't want to put a number to it, but it's maybe 10, 20% of the water migrates down vertically through leakage, but the bulk of it comes in through recharge. And so why is our water so clean? Well, because it's flowing through this granular material that acts like a filter. And plus, you know, so it's traveled a long way and it filters out those contaminants before it gets to you. Okay. Now, there's some things that don't get filtered out. There's, you know, you can put, there's some contaminants that don't get filtered out in water, especially dissolved things. But that's the basic answer.
Okay. This is a relatable question. What percent of the Florida aquifer supply is via Appalachian range versus groundwater recharge? So is Is it pretty much all recharge, or does any of it come from the Appalachian Range? Or
None of it comes from the Appalachians. They're too far away.
gotcha.
The mountains themselves, the Blue Ridge, are up here. So this outcrop belt here is the recharge. So it's basically Augusta, Macon, Columbus. That's where the water enters the system, most of it. Okay? Not further up.
Okay. All right, so here's a question that teeters on policy and science. So if anybody's been paying attention, EPD put out a proposed restrictions what word that's not the right word.
Special conditions.
Special conditions for the proposed new wells. And there's a 5-mile radius where there's going to be a fund set aside, I guess, to help people that have unreasonable impacts, which they didn't define what those unreasonable impacts are, but I assume that is having to lower your well is what they're talking about. And so the question is a 5-mile radius a reasonable consideration with the amount of water these wells are going to? Yeah.
Before I answer that, I read that too. EPD is going to hold, you folks know, a public hearing in Statesboro at Southeastboro High School on February 26th, and they're going to give the details of all this. But basically, from what I read, they're going to have, they're suggesting that Bryan County and Bullock County develop a fund will offset the costs for people that would line within that cone of depression to lower their pumps. And they also indicated they're going to have some approved independent party to monitor the water quality. One of the things that I suggested that they do to see if we're having any vertical saltwater intrusion is to monitor on a monthly basis the chloride content of these wells. If that chloride content starts to change, it means you're pulling in undesirable water from somewhere else. And EPD did, if you read the second condition, they are indicating that they want to have a fund to mitigate that. So we'll see what they have to say on that. Now, in regards to this 5-mile or 2-mile radius, whoops, I don't want to show you. Oops. Here. These drawdown cones, as I mentioned, the radius and the depth of them depend on how much you pump. So, and it's easy to calculate this. So EPD, I'm sure they've already run the models, but you input into these models how much the pumping rate is going to be, the permeability and porosity of the material, and we can calculate with a fair degree of accuracy the amount of drawdown that you get from any distance away from the well. And at some point, there's no drawdown. That's the zero line here. So if they've put a limit at 2 miles, someone's already done the calculations. That's probably the cone of influence of these wells. Okay. And that's because they're only pumping about 1.5 million gallons per day each. Now, if you're pumping 50 million gallons a day, the cone is going to be a lot larger. Okay. And I would mention too that let me bring this up too. Remember what I said that if you have 2 adjacent wells, the drawdown is cumulative.
Mm-hmm.
One thing to keep in mind when we look at the Floridan here, this drawdown cone is not from a single well. This is from a whole series of industrial wells and municipal wells that collectively create this cone of depression. So this is not a single well. This is collectively from a bunch of wells close together. Okay. And so the reason this has such a large influence because you're adding together all these millions and millions of gallons of water that's being pumped. It's all a cumulative effect. So it's not a single well. It's a series of wells throughout that region.
Oh. All right, we have about 15 minutes left and a lot of questions to go through. So
I'll try to go quicker.
Yeah, we have about 10 more. Let's see. Is Tybee Island in danger of saltwater intrusion like Hilton Head?
Yes, they have. The USGS has done studies offshore. They've done sampling offshore, and they've done some a deep well test. And saltwater is coming down through the aquitard into the Florida, but it's very slow. It doesn't have an open breach like it does in Hilton Head. There are some places where it depends on that breach. Okay, otherwise it's got to move very slowly through the aquitards, and that's a slow process. So one of the things they're concerned with are other channels like they see in Port Royal Sound. But yes, the answer to that, yes, it is coming, but it's very slow. But they would be the first to encounter this salt water coming in from the ocean.
Gotcha. All right. Not quite sure I understand this question. All right, you want to answer that one? So is it and there's a couple of people who had similar questions. So is it possible for the Floridan aquifer to be contaminated from open sinkholes?
Yes and no. Like on St. Catharines, the key, remember these aquitards are very tight. They don't let water flow through them. So what I keep referring to is a breach, like these sinkholes, that's a conduit to let water move through.
Okay.
So when the water pressure was greater in the Floridan, you couldn't contaminate it because water was leaving through this breach. Today, if you're in an area where there's downwards leakage, like a lot of places are today in Florida, yes, those sinkholes that we see provide an avenue for water to move down into the upper Floridan. But in Bullock County, I can tell you that the flow is not downward, it's upward. So those sinkholes we see in Bullock County should not be causing anything to happen to Florida because the pressure is still positive.
Gotcha. All right. So that answered the second part of this question. The first one is, would a spontaneous demand of water, such as a fire at the port or anything, cause any issues? I would assume not. That would be.
Now the volume of water for that is pretty small.
Okay. All right. So that kind of leads into one of the questions I had that is another issue tangentially related to the well issue, but certainly related to all the development and impacts to the Florida aquifers. There's a proposal to deepen the Savannah Port again. So what impacts would deepening the Savannah Port potentially have on the Floridan aquifer?
When I first came here in the 1990s, there was a large study, and I was involved in the technical advisory committee for that very subject. Let me find this other slide here. Okay. This is not a Savannah River. It's not shown here, but it's similar. Okay. And so this the situation with the Savannah River, they would have to deepen the channel to bring in bigger ships. And the concern was this is what's protecting Savannah. You don't want to create a potential conduit close to the pumping center, and that's what would happen. So the concern was the deeper you make this channel, the thinner you make this protective layer, which is going to increase the saltwater intrusion. This is still the main entryway. It's open. It's like an open sewer. Here we still have some protection. And so they want to deepen it a few more feet. Well, there's still quite a bit of aquitard thickness, but they're still risking increasing a little bit of saltwater intrusion. The bigger problem is it's going to allow saltwater to move inland further during high tides and cause salinization of some of the fisheries that within the Savannah River. So the deeper you make this channel, tides can push that saltwater further inland. So that's going to be an immediate impact, and it's already taking place as we've been dredging the channel ever since ships been going out of Savannah. But yeah, the problem is we're making it a little deeper and thinning our protection.
Yeah, and if that protection is breached, then that'll just reduce the pressure. That'll just be another kind of a huge leak in the tire, so to say.
Yeah.
Yeah. Okay. Had a question that's probably kind of hard. That's very case by case, but yeah, it's really about, let's say if you have a shallow well that's about 90 feet and 30 years old, would you need to lower your pump or would you have to dig a new well? And I guess that'd be very specific to how deep the original well was dug.
Well, I have to talk everything from a picture.
Right.
Here. There are people in Bullock County that have shallow wells. I have a colleague who has a 100-foot well that is not down into Florida, and so they drink from the superficial aquifer. It's unconfined, but it's deep enough to still provide safe drinking water. So if this individual's well is 90 feet, that tells me that it's not down into the deep system, which means this proposed well should have no impact on theirs, because it's in a different aquifer. The people that have to worry about lowering their wells are those that are sharing that same pumping horizon. Let me go to this one. This is better yet. Here. So this is Bullock County. This is Statesboro. Everybody that has a Floridan well has a well that goes into the limestone that's 400 feet down. There are people, though, that are using this shallow aquifer for water as well. So if you have a shallow unconfined well, this pumping is not going to affect you. It should not be.
Yeah, if you're on a shallow well, you probably have other
worries. Yeah,
you have other worries with contamination from surface water pollution, for sure. All right, we have another question, or several come in. One is, how can we best gauge how much more withdrawal the Floridan can sustain before coastal counties and inland counties lose drinking water supply?
Repeat that again. I'm sorry.
How can we best gauge or determine, I guess, how much more withdrawal the Floridan can sustain before coastal counties and inland counties lose drinking water supply? So,
well, this is a very prolific aquifer system. There's a vast amount of water down there, and like I said, you're not going to dewater this. The water is still going to be there. The more we use, the more drawdown we get. And what that means is you're depressurizing the system. When you depressurize it, more bad things can happen. You can bring in water from other places, but the water itself should remain abundant, and it should remain high quality. But the more we depressurize it, again, the more bad things can happen. Just like let me go back to this. This was a highly pressurized system in the Great Plains, and we depressurized that from 90 feet above the land surface to 120 feet below. They're still pumping water from it. But when it's just like driving on a flat tire, you're inviting bad things to happen. Is you still got air in it, but you can introduce things into the system that shouldn't be there. But we're nowhere near the amount of depressurization we've seen in other aquifers. I'm not saying this is a good thing, but the aquifer is full of water, and it's over 200 feet above the top of the aquifer here in Bullock County. There's a long way to go. There's a lot of room for withdrawals. But I'm not trying to be a promoter of the project, because this whole thing is bringing a lot of changes to the rural communities and people that have their own way of life and irrigation systems. I'm well aware of that. So that's a different issue. Just talking about the science itself. The aquifer can stain every city. Claxon, Statesboro, everybody has large Floridan wells like we're putting in here to supply their own citizens with water. Like Georgia Southern has 2 or 3 of them itself just for campus. So these aren't that uncommon.
Yeah, that kind of goes back to a question I had about the pressure and the reduction of that. And I know I talk to people all the time that talk about all the springs that used to be in the Ogeechee River Basin that have stopped flowing. And I assume that has to do with the pressure.
Correct.
And so there's obvious surface water implications that, a lot of people will try to disconnect the flows in the rivers and our tributaries from the groundwater, but there's other implications. I know there's a lot of research being done that over the last several decades, the average volume of water in the Ogeechee River has decreased a lot, and that's just several different things. But one cause is this reduction of input from the Floridan aquifer through these springs. Is there any estimate about how much water has been reduced, and do you have any thoughts on the implications for surface water from overtaxing and using this aquifer?
Let me say this too. If we go back to this diagram I showed earlier, remember this used to be all blue?
Mm-hmm.
So all these streams used to be fed water from the aquifer, the deep aquifer. Okay, these were spring fed because they were where the positive artesian pressure. This is the area where we've had the big impact. All this, the whole coastal environment has lost that upwards flow of artesian water from the Floridan. So there's all kinds of springs that have been dried up. So those are really significant. I don't want people to confuse what's happening in Savannah, which is highly unusual to have this big a cone. This is a world-class cone of depression. This is huge. And what we're seeing of the cones of depressions on campus, Evans County, at Claxton and Statesboro, and these 2 wells, 4 wells, they're not going to be anything of this scale. Okay. I think that's what concerns people. We're going to see this type of cone of depression. Look at these smaller ones here. These are all from industrial withdrawals. Okay. We're not using the water anywhere near this scale. Okay. So this was kind of a off the charts example, and we're not going to see this kind of cone of depression in Statesboro. Now, that doesn't mean bad things can't happen, but it's not at this level.
Gotcha. All right, we are at 8:30. We have one more question that came in. So if you're willing to stay just a few minutes.
Yeah, I'm not going
to. We'll go ahead and knock it out. This person says the Georgia Department of Transportation is studying the possibility of drilling tunnels up under the Savannah River. Wouldn't that be impactful to the confining layer? Thinking it more, could that create a fissure or a breach? Could that kind of cause issues that are unforeseen with the port deepening and drilling through and tunnels? So are you familiar with this or have any thoughts?
No, I haven't. I'm not familiar with that, but I will say this. I have better diagrams for this, but what's underneath the river is the aquifer. The aquitard is fairly thick there, and it gets thinner as towards Port Royal. So if they're digging down in the Savannah River, it's like this. They're not in the aquifer, but they'd be down in the aquitard. And I'd have to look at the details of that. So, but yeah, anytime you excavate some of this, you're thinning that layer of protection.
Mm-hmm.
But I don't know the details of those tunnels. Okay.
Okay.
And keep in mind, they're small diameter compared to the scale of this on the landscape issue. These are, even a 20-foot tunnel is fairly small in diameter.
Gotcha. Okay. Well, I just want to thank you so much for taking your time to do this and helping to educate us and talk about these issues. As our coast is developing and our demands of water are increasing, we're going to have to rely more on surface water, manage this aquifer. And so I suspect this will be one of many conversations that need to be had over the next decade or so to make sure that we're using our resources wisely. And I'm very grateful for you spending your time with us today.
Glad to be here.
So with that, we will end. I want to thank everybody for coming. Thank you guys for attendance. We have this recorded. We'll share it if you missed anything or attended late. And with that, we'll end and thank you all. Goodbye. Good night.
Take care, everybody.
Bye.
Bye.